Hello everyone! Wow, nice group of friends today. Ruth, how are you doing? Smiling and hey,
Smiling always.
hello,
Thank
good
you
to
very
see
much.
you again, Matthias. Wow, we have a great group of people here. Let's get the ball rolling. Let's start. Ladies and gentlemen, welcome. Welcome to the epic online technology meeting on 3D printing. My name is Jose Pozo, and I'm here with Francesca to spend a beautiful Friday afternoon, evening with you, 2.5 hours of 3D printing world. This is actually the number 17 of the Epic Online Technology Meetings. We have covered many topics so far, and we still want to cover a lot more. I really have something for you to know, which is that we're going to continue the online technology meetings all the way to the end of July with 3 meetings per week, and we'll come back in September with 1 meeting per week for as long as Epic lasts, and that will be several lifetimes. So we are very happy to tell you that right now we have 557 members of Epic. For those of you who are keeping track with the Epic Online Technology Meetings, you see that every time I announce a few more, we keep growing. Thank you so much for the industry to get the support that we have, and we can keep doing amazing things. Amazing things like the online technology meetings, amazing things like the present meetings. For those of you who have never experienced an Epic present meetings, when the situation goes back to normal, when we reach the new normal, they call it now, we have great meetings planned. For example, we have a meeting at Siemens to talk about 3D printing of metal. This will be 29 and 30 of September in the beautiful city of Finspång in Sweden. Things will go back to normal, I'm sure. And in the meantime, we cannot travel. We go and we stay at home with the online technology meetings. We can check market reports. All of you are Epic members. We have great market reports in the extranet. 17,000. I think Carlos got crazy and counted it. It's 17,000 market reports, data, graphs, view graphs, charts, all of them for you. We have bought last week the worldwide market for lasers. This is the most expensive market report that we have, also the best market report available in the market. We're giving it for free to all the Epic members. It's from Strategies Unlimited. And also 2 weeks ago, we bought the Global Metal Additive Manufacturing Market 2022-2024, which is actually quite a nice read if you want to see which application fields are growing lately and what are the increase in volume manufacturing by many of the companies. Actually, was quite amazed to see the numbers already show. So it's actually quite a good market report. Something really cool to tell you as well is that we have the biggest website of finding a job in photonics. So all of you have jobs, but all of you have also job openings in your companies. So for those of you who are looking for companies, who are looking for people to fill these job openings, we have actually proactively scouted the job openings of the 557 members of Epic, and we have put them in the website here, and we are actually promoting this with recruiters all over the world to find the best people to work in photonics. I have a job in photonics, I love it, I don't want any other, and I want to promote people to keep working in photonics. And that's all I had to say about Epic. Now let's talk about the reason we are here today. We are here today to talk about 3D printing. There are many definitions on 3D printing. 3D printing, there are many people who say that it's just additive layer manufacturing. For me, 3D printing is making things in 3D. And for this, I include additive and subtractive manufacturing. Is my definition. Maybe it's wrong, but it's mine, and I love it. I would like to thank, first of all, the sponsors today. 2 sponsors, 2 rocking sponsors, DMC, all the way from Lithuania. DMC makes software that controls 3D printers. Actually, they can control multiple Galvo scanners to print actually at very high speed. I've been visiting them. They are really fascinating. You know, when you have to contact multiple lasers, multiple Galvo heads, multiple extruders, or any other tool, DLP, special light modulators, these guys know what they are doing. It's the best software for machine control there is in the market. And Obducat, all the way from beautiful Sweden. Obducat is a company. It's actually a world-leading supplier of lithography solutions for advanced micro and nano patterning of surfaces. So you're looking for a partner for nano imprint manufacturing in the volume production. These guys know what to do from the prototype level all the way to the volume production level. Obducat, thank you very much for sponsoring the event this Friday afternoon. And with this, I would like to give the floor to Francesca Moglia. She's our expert on laser and the person who does the best job explaining what's in the menu. Francesca, ¿qué cosa mangiamo?
Thank you, Jose. So welcome also from my side. So it's really great to have this first 3D printing event, I guess, if I'm not wrong. So we brought together, as Jose said already, different materials. So, and 3D printing is growing in 3D, as Jose said. So this is a bit our background. So here we can see our agenda, but maybe, Jose, we want to see better this one. Exactly. That's what usually we prefer to show you. So basically, as I told you, 3D printing in this event will be a bit broad. So that's why we have a family of EPIC members that actually are really strong in our community. So those belonging to the 3D printing of micro optics. So that's why we have this group of companies committed into photon polymerization. So we have Nanoscribe, multi-photon optics, and Pilot 3D. But then we also more on the side of nano imprint. As already Jose said, we have Obducat, but also Zeus micro optics. Then there's green printing, substrate laser writing, like Heidelberg Instruments is doing, and then we have our fantastic pilot line, fabulous. So that's why supporting the 3D printing of micro lenses and micro optics in this and funded by the European Commission. But then this is our experimental place. So now really EPIC wants really to commit more with 3D printing of metal. So that's why we have these 4 fantastic speakers today. So from IMD Engineering and OEB from Italy. So both offering services and using 3D printing devices. But then we have also EOS, very famous manufacturer of machines, and also committed in 3D printing of plastics, not only metal, and then Aconity 3D that has a multiple offer of services in the field of 3D printing of machine, but also services. Then, of course, what can we do for these speakers? Of course, need also to talk with all the full supply chain of this fantastic technology. So that's why we have beam shaping and process monitoring people here. So we have from near infrared technologies showing us then later also what does it mean to control these complicated devices. But then we have also feedback highlights, Excelitas, Synoptic, and Oxford Instruments that, of course, have all the optics needed and fibers for this kind of processes. Then we need, of course, design, so CubeTech International and VisitTech Engineering for all also the platform and services. And then the R&D, of course, without the R&D behind all that is done in research about 3D printing, we would, of course, miss a lot of the last development. So that's why we have a lot of Fraunhofer institutes, so ILT, IOF, and ISE, but also AMEN will tell us a bit later also about another European funded from the Commission project. Then UANEUM and Haile is also very committed, and it's a 3D&T. Then, of course, the end users, 3D printing products that can be used everywhere. So, for example, advanced electro-optics packaging, medical application is also in space. So hopefully we can talk also with these end users. And then you cannot miss laser manufacturers, of course, so and system engineering. So we have all the supply chain also from the laser side. And then automation, and this solution for automation and position are really important for, so like PI and FICON-Tech. And then, of course, the market. So we see we have 2 consultants, so they're all really interested in talking about 3D printing. So let's speak, and then let the first one speak. So Jose, first you, and then the agenda goes on.
Al dente, Francesca. Wow, now you can breathe. Now you can breathe. You're really good at speaking fast. I don't know who you're learning from. By the way, we also would like to remind the people in the YouTube channel, because we are broadcasting this meeting in YouTube, that you can post questions in the chat. But most important, if you want to get in touch with any of the participants today, all you have to do is send me an email, jose.pozo@epic-asoc.com. That's valid for the people in the Zoom channel as well as the people in the YouTube channel. If you want to get in touch with any of the participants, jose.pozo@epic-asoc.com. The purpose of this meeting is to find reasons of working together. Once more, I would like to thank our great sponsors. You guys rock. Direct Machine Control, DMC, and Obducat. And with this, it is time to get the ball rolling. It is time to start with the fantastic program today. And I want to stay in the Netherlands first. I want to give the floor to our EPIC member, Berenschot. Berenschot has been with us already for quite a while, talking about building companies together. That's what they do the best. But Onno Ponfoort is one of the people that knows the 3D printing market the best. And he would like to start by telling us, putting this meeting in perspective. Onno, goedemiddag. Thank you all for being here today. The floor and the attention of everyone is yours.
Goedemiddag. I will try to share my screen. Let's see if I can do that.
I'm sure you can. It's the green button at the bottom of the screen.
Yeah.
It's a beautiful day in the Netherlands, by the way. Sunny.
There we are.
There you are.
Great. Thank you, Jose and Francesca. If I can speak as many words as you can do in 1 minute and 6, I think it will still be an interesting 6 minutes that I can present. I'm the practice leader for the 3D printing at Berenschot, involved in the market for some time. Started in roughly 2004. I think most of you might not know Berenschot. Berenschot is a consultancy in the Netherlands. We're the oldest independent one, founded in 1938. Roughly 350 people, headquarters in the Netherlands, also offices in Belgium, and some partnerships around Europe, especially. I'm the practice leader for 3D printing, active in that arena for over 15 years now, and we're primarily looking at the economic and organizational aspects. So I'm not taking it from the technology side, but I'm taking it from the benefit side. What I always say is there are people who answer the question, can we print it? I normally help my clients answer the question, should we print it? Is it really necessary to print it? Does it give benefits? I have some experience in this field, joined in a number of international projects, demonstration projects, and innovation projects. We started in 2014 with the so-called custom fit project, which I think is an iconic project in the European arena. In this project, we looked at elements of the supply chain, elements of setting up an order process, but also looking at building economic development programs with 3D printing. We see a lot of economic development agencies looking at the possibilities to attract new companies and set up an industry with 3D printing. We've also developed training and modules and workshops. And the latest project that we were involved in, I'll say something about it later on, is the development of a guideline for certified 3D printing of spare parts in oil and gas. What we're also always looking at, and I think that's also something I'd like to talk about with those in the audience and the other speakers also, is what are the benefits of additive manufacturing? We see three main arenas. Of course, we see market opportunities. We see companies looking at a quicker time to market with 3D printing, customizing parts. But also one thing which is very important in market opportunities is that you can really create a much tighter lock-in with your customers by a co-creation of 3D printing. It's an opportunity that I often see that people, let's say, miss out a bit on. Other aspect is production efficiencies, not only in the form of prototyping, but also in the form of developing tools and possibilities to actually ease the production. And we see supply chain benefits, although it very often is still a promise and not so much something we see happening on a large scale yet. And with large scale yet, I mean digital warehouses, allowing companies to produce parts quite close to the area where they should be used. But these are mainly the benefits that I see that companies are looking for 3D printing. The only unfortunate thing is I've not seen too many parts yet that will help you to actually capture all of them. So we very often look with companies to what are the possible benefits and which are the 1, 2, or 3 benefits that you should actually go for. What is the best option for your organization? Something about this JIP program I told you that we were involved in. I started with a quote of Gisle Rurvik of Equinor. Used to be Statoil, now it's Equinor. He indicates, before AM parts see service in oil and gas, it is critical that we understand the properties of AM builds. Guidelines and standards will have to be developed to give engineers the confidence that the quality of AM components can be relied upon. In a highly restricted and standardized industry like oil and gas, but also in automotive and aerospace, it is really essential that you know that parts produced by 3D printing really comply with standards. And in oil and gas, that was not the case yet. So we teamed up with DNV to build a guideline indicating all the requirements to introduce AM for oil and gas. That guideline was issued earlier this year. So now there is basically a handbook that companies in oil, gas, and also maritime can use for printing high quality parts by WAM and laser powder bed fusion. At this moment in time, we've kicked off a new project, by the way, for other 3D printing technologies like LMD and electron beam and binder technologies to also produce this guideline for quality printing. What we did in that project was what we call the toolbox part. We managed the production, selection of parts and materials, but we also assessed the impact of 3D printing on the bottom line. That's something I want to briefly introduce to you. We basically built a model to help companies look at each and every value stage in the value chain and look at what is the impact of 3D printing versus traditional manufacturing. So right from order intake, via design and production preparation, all up to production, testing, but also the use of the part, logistics, maintenance, and end of life. We have now a model available that can help you assess what's the impact on the bottom line and what's the variance with traditional manufacturing. And that's necessary because very often the cost of printing a part is known and also very often higher than a traditional part, but the benefits are only captured in the use phase. So this is a somewhat more difficult business case than when you could straightforward just look at production prices and select those which is more efficient. You really have to look at what does 3D printing bring you in the use phase. So we have a full model, way too large to show you, but for each and every stage we have an overview of what are the traditional cost drivers and what's the cost base, what are the extra activities due to AM, and then we can build a variance on all these elements, looking at all kinds of cost drivers. We also have a large sheet with all cost drivers available that we can link to. So labor cost, material cost, machine depreciation, transportation costs, warehousing costs, well, you name it. We have it in a separate file, and you can basically fill out our form and together with us look at what might be benefits. You can use it for simulation, and you can also use it to build your investment decision business case. I think that last thing is also an important one. Also something I'd like to talk about with the people in the audience is, should you go for investing 3D printing? And if yes, should you do that via buying your own machines? Or is it better to work with service providers? Or is a mixed model of those two the best solution for you? So that's the arena that we work in, and especially the discussions and inspirational talks with people on how can we use 3D printing and what are the benefits that it will bring to my organization are the ones that we can support, and I will always get very enthusiastic about. So if you want to touch base with us, you can do so via Jose, as he indicated, or directly to me at Onno.Ponfoort@Berenschot.nl. And if you want to give this model that we have a first try, you can go to berenschot.com/3dbim. And there are 2 tools available that give you a small snippet of what the economic model can bring to you. Any questions now or later? I'm open to it.
Thank you very much, Onno. Really nice overview of your activities and also with already some hints to activate our audience. So are there already some questions, or I can comment myself? So maybe I comment myself because there were 2 things really interesting that you mentioned. So oil and gas market. So basically, guys, we have to open ears. If someone still didn't join in this market, probably we have to. Although maybe there is someone already in the room with some past experience about it. If you want to comment on this, please. And also the other thing is exactly what Onno asked at the beginning, at the end of the talk. So if someone wants to comment about if it's better to sell a machine, or to buy it, or to sell services. So I would say here there is Yves sitting from Aconity 3D. He probably knows the 2 sides of the experiences, right? So you have the machines, but you also offer the service. What is your feeling in this? What is best for which customers, for example?
Well, what is best is always difficult to say. I'm not an attorney, but I keep saying it depends. So it depends if you build core knowledge in your parts, which you don't necessarily want to give out to a service provider, or if it's a standard part made out of any kind of standard material, which you can easily give to a service provider. So I think the truth is, like what Onno said, somewhere in the middle, and it depends on your specific application.
Okay, then Onno, they're all agreeing with you. So
and if I can add to that message,
sure.
You know, when you really want to use 3D printing for a number of different parts, then very often you would also have to reach out to different technologies or different materials. It's going to be very cost intensive if you want to do that all in-house. So I think that most companies will always have a hybrid model where perhaps some things they do in-house, but for other things they have to reach out to service providers.
Definitely. So it's similar then with the sheet metal industry. It used to be core knowledge for automotive manufacturers, but nowadays you can buy laser cut sheet metal basically anywhere. Still, BMW has sheet cutting machines within their manufacturing structure. So yeah, you're absolutely right.
Very good. So are there any questions or any further comments? Because if we all agree, it's not good. Because otherwise we shouldn't have, we cannot meet just to say, yes, you're right. No, I'm joking, of course. It's good that there is a background of a common feeling. Because if there is, it's not the case of questions, maybe we can already move to Tadas from DMC, and maybe you can introduce yourself. So you're not sponsoring only, but you're here in the room. So maybe you would like a bit to introduce with your words what DMC is doing, so that we just announced it at the beginning, but you tell it for sure better.
Hey, thank you. Hello, everyone. At DMC, we are creating software that controls laser machines, and part of that is controlling laser 3D printing machines as well. So usually some powder bed-based system or some slurry bed systems. And we control all the machines, so Gauss scanners, stages, laser sources, various sensors in there. We slice the models, take care of hatching, and so on and so on. So basically all the process from when you have the model to final cooling of the chamber and when you take out the part.
Very good. Then I guess after this brief introduction, we maybe jump back to our agenda so that we keep it rolling. And it's the turn of Andrea Buccelli now. So we have our CEO of MD Engineering presenting their activity in Brescia in Italy. So please, Andrea, feel free to share the screen and the floor is yours. Yes, we hear you. Yeah, and the screen is coming. Very good. Yes. You have maybe, listen to me, you have some windows maybe in front of the slides because some part of the slides are covered.
Yeah.
Yes. On the right side, maybe you can remove, there is something that we don't see, but we see a shadow. This may be us, it's probably Zoom. It's us. And so you cover the slides like this. Maybe you, yeah, this looks good now. Oh, it's better. You cover just the corner of it. Now it's good. You can start, I guess. It's okay.
Thanks. Good morning. Thanks, Francesca, and all the EPIC staff for this opportunity to present my company. Nice to meet you, everyone. First of all, I need to analyze our acronym AMD, Additive Manufacturing Development, or we want to help you to develop your additive manufacturing business, starting from engineering. If you see in the left of the slide, fire is the aim, additive manufacturing. You need 3 elements like in additive. Beside of the triangle, there is 3 elements necessary for the combustion.
Ciao, Andrea. Can you do me a favor? Can you press Control L? Control L.
Okay. Control L. Okay.
You should go to full screen. Select the screen and press Control L.
Oh, this is a top of large.
Okay, well, that's okay. Just go ahead. Sorry.
Sorry. Okay. Well, there is a component. I think we can read the powder. The trigger search is the printer, laser, electron beam, direct energy deposition. And there is the fuel. Fuel is engineering. For us, engineering, design for additive manufacturing, DFAM, is the fuel of additive. And without this element, additive, I think, don't burn. Our approach, our first goal with our customer, we start to analyze together what they want to engineer with additive technology and develop together a new kind of business or a new kind of of component. To do it, we have obviously software, we have topology optimization, final element analysis, and computational fluid dynamic. Obviously, there is the people who work in MD, the engineer that decide the right way and the good strategy for our customer. For additive manufacturing, there is in the right of the slide, there is a lot of sector different for business, but for additive manufacturing is so similar because if you have inside three of this feature, so I think that you can take to develop your business so with additive manufacturing. For example, we can take automotive and fashion. Is very different, but what they have in common. If I see rapid prototyping, I think fashion, during the fashion show, many people run have to best creation. Small batch production or spare parts in automotive, for example, being able to get the physical idea of a component or a car or a bus or a truck in a short time. Top of the performance, I think usually in automotive, fuel saving or better energy efficiency. So like we 50-50 and exclusive design, I think obviously fashion. When there is something of special, you can analyze additive technology. Well, now we come to the second slide. Okay, this is the second slide. This is our case study that we developed years ago for our customer. This is not the last because obviously we have an NDA, but this is a good case study for me to understand how the additive manufacturing push, because in the right there is an old heat exchanger, is composed welded and composed from multiple parts, but with additive manufacturing you can fuse it together, and it's possible only with additive. There is no other solution. See, the characteristics is more similar, but there is a characteristic very important. The power. In the first, in the right, there is 7-8 kilowatt. In the second, there is about 50 kilowatt. We tested, obviously, I think after COVID, and I give a review. Well, now in the first slide, we are a consulting, an engineering consulting, and we analyzed with our client, obviously, the job together, and decide to develop the components with a service bureau or start to give a business plan together and a complete layout from subtractive and additive technology together. And we can grow up with a customer new factory of the future. This is our focus. So now we want to combine all the aspects, subtractive and additive technology, because if you integrate together in your factory, this is a good solution to have a unique shape and a big performance. Well, I finished. Thanks for your attention.
Grazie mille. Thank you for a great presentation. I think there is a lot of room for cooperation. Andrea, this is your first ever EPIC meeting, so there is something that you are not aware of, but the rest are. When you present technology like this, you always get the same question. What can you do for them, for the rest of the people in the room, the whole supply chain, and what can they do for you?
Well, I think that we can cooperate together, because additive manufacturing need to grow up, and alone we can go away. Additive manufacturing is a combination of a top of powder, a top of printers, and a top of engineering. So I think the unique way is collaborate together in a unique direction.
Fantastic. So I'm going to introduce you to some of the people who want to collaborate with you. And I'm going to go to the capital of optics in Europe. That's Jena. And I have Eric from Fraunhofer IOF. Thank you very much for joining this afternoon. How are you doing, Eric?
Thanks, I'm doing fine.
Hello?
You're wearing a beautiful mask. Is that because of the virus that I heard is going around? You look fantastic with it. What did you join this meeting and what kind of cooperations do you expect to do afterwards?
I will later talk about the printing of optics, and I'm in particular also interested in what people talk about machinery for printing metrology, for printing planning of printing, so software and these things. For now, I have seen most types of metal part printing, which can also be relevant for optics, metal mirrors, for instance. But I will later talk about the printing of refractive optics.
And don't worry, because we're going to talk a lot about this. Did you see the agenda? But one thing that Eric really pointed out that they wanted him to say was the word metrology. Andrea, what kind of metrology solutions are you aiming to have? If you could ask for the Santa Claus Christmas list of metrology, what kind of things would you like to ask these people?
But I think that additive manufacturing need to have is a good way for metrology, because you need to grow up metrology for text the component in the end of the printers, because the printer have a fusion is not complete. You have to machining, to finishing, and then so you need to have a good machine to test it.
Have you ever been to Austria? Because there's a city, Graz, which is beautiful. And there is a center called Joanneum Research. And one of the key people in Joanneum Research on 3D printing is here in the room with us this beautiful afternoon. How are you doing today?
If this is, can you hear me? Yeah.
Yes, loud and clear.
Okay, fine, thank you. Well, surprisingly for me, it's also personally the first time that I'm at EPIC meeting, although Joanneum is a standard member. And also I'm before worked in some institutes that are members of EPIC, but it's a coincidence. This is the first time that I participate.
What do you do in a meeting like this? What kind of cooperations you want to do?
Basically, my first intention is to see what other people do, especially along the value chain of optical optomechanical setups, starting from lasers down to the processing, because there is always something interesting that you can learn from all these people. And also as a application, let's say, engineer in the bottom, I always look for something of the optical elements that are developed recently that can make my life easier, both in laser welding, laser cladding, or additive manufacturing, because there is always something new.
So to make your life, the life of Eric, and especially the life of Andrea, easier, the next presenter is here to help us in the EMEA band. Let's go to Madrid. How is the weather in Madrid today, Rodrigo?
Not too sunny indeed. I think it's about to rain.
Talk to us about the EMEA band and what can you do in the 3D printing sector. The floor and the attention of everyone is yours.
Thank you very much, Jose, for the introduction, and good afternoon to everyone. Well, my name is Rodrigo Linares. I'm from the company New Infrared Technologies, and before presenting the solutions that we offer to the 3D printing value chain, I would like to start with a very short introduction to our company. So New Infrared Technologies, we are a company located in Madrid. We develop and commercialize solutions for real-time process monitoring and the smart control of industrial processes. We are a vertically integrated company. That means that all our solutions are based in cameras that we produce ourselves, manufactured with a unique technology. These cameras have detection in the 1 to 5 micron, high speed, and can operate without refrigeration at room temperature. We are members of EPIC, but we are also members of ADIMAT, which is the Spanish Association for Additive Manufacturing and 3D Printing Technologies. So in this slide, you can see what infrared technologies can offer for the 3D printing sector, but I can summarize it as high-speed infrared cameras and solutions for 3D printing process monitoring, control, and quality assurance. All these systems are targeted to integrators, solution developers, and end users involved in this 3D printing. I will present them in the next slides, but I would also like to mention that we have a strong collaboration with the industry in the 3D printing field through H2020 projects like Integrate. I think there will be a speaker afterwards talking about this project, this pilot line, and Custodian. First, I would like to start with Clamir. This is a solution designed to control laser DED processes like laser metal deposition and or laser cladding. The way that Clamir operates, it makes a continuous monitoring of the melt pool geometry with the camera at high speed, and then it closes the loop and controls accurately the laser power. With this, we assure the quality and the repeatability of the process because some effects are avoided, like overheating of the part. The system is compatible with most of laser sources, optics, and powders. It's a standalone solution. It doesn't require a permanent connection to the PC because we have combined here the infrared camera, the processing electronics, and the control electronics, everything in the same system. We have currently multiple customers all around the world that have taken Clamir as their solution for LMD and cladding process control. I would like to remark that this product was awarded with Innovation Radar Prize in 2018 by the European Commission in the category Industrial Enabling Technology. Here you can see that Clamir is a very compact system. It's easy to integrate in most of the laser optics used for laser DED process. Here you can see photos of the system installed in optics from Trump, from Laserline, and from Precitech. I would like to show you the benefit of using Clamir in the control of the laser in LMD processes. You can see that here, an uncontrolled laser power can lead to a defective part, like in the sample of this tube, where there is a clear effect of the overheating that prevented the part to grow, compared to the one in the left, where the process has been done with power control, and you can see that the part could grow perfectly without interruption. Of course, one of the strategies that the manufacturer can follow to avoid overheating is to stop the process and let the part cool down, and then restart the process again by deposition more layers. But of course, this causes a stop of production and has a direct impact in the productivity. With Clamir, it's possible to have a continuous and high quality manufacturing process, such in the cuboid that I'm showing here. Here you can see how Clamir was controlling the laser power, that's the blue line that you can see here, while maintaining the melt pool width constant. And with this, what has really the consequence of this is to have a continuous processing and a high quality manufacturing process. Also, Clamir can help you to optimize the process and improve the productivity. It's a very powerful monitoring tool. Here in the images, you can see the 3D reconstruction of the instantaneous thermal gradient of the same part built with control on the left and without control on the right. You can see that without control, there is an accumulation of heat when the part, as the part is being built towards the upper layers. And all this, of course, has an impact in the final finishing of the part that is being manufactured. Here you can see the difference between the two parts with control and without control on the right. All this data has been acquired and analyzed thanks to the data logging capabilities of the system. I would also like to tell you about this other system, I3MS, which stands for Inline Infrared Monitoring System. This has been designed for a continuous monitoring and measurement of the melt pool and heat affected zone width to ensure the monitoring of the process quality. This is also a standalone system, and it has two features. One is that the melt pool width is available as an analog signal, and second, that the user can set up two alarms, two alarm levels, one for warning and one for failure. And these signals can be connected to a PLC to take corrective actions. This system is of application in laser DED processes like with powder and wire, or for wire additive, wire arc additive manufacturing process as well. To finish, I would also like to introduce the Tachyon 16K Camera Plus. This is a high-speed mid-IR infrared camera for 3D printing process monitoring. with a resolution of 128 by 128 pixels and a maximum frame rate of 4,000 frames per second. The camera has machine vision interfaces like GigiVision and is GANICAM compliant. It also has the capability to acquire the images in a snapshot. And one 3D printing method that can benefit directly from these features is the powder diffusion process, which is very dynamic and requires very high frame rates. Here on the right, you can see the camera coaxially integrated in a PBF machine. Here also the image of the melt pool taken during the process. This image can be analyzed to take relevant information like dimensional information and infrared intensity during the process, and study the relationship, for example, with the movement on the scanner or the applied power. Or, for example, study the instantaneous cooling rate in real time. In here, the main advantage of our cameras versus the CCD cameras is the higher dynamic range and the capability to detect lower temperatures. So with this, I finished my presentation. I hope that you could get a better understanding of who we are, and what we can offer to the 3D printing chain. I also would like to say what we will need from the supply chain. Well, you can see that all these systems, all these laser systems, have been optimized usually for visible cameras because of the low penetration of the infrared into these applications. So even though our cameras, they can operate with the current configuration, it would be great if all these optical systems like mirrors or laser optics would be adapted to the infrared, because of course we see a huge benefit of introducing the infrared monitoring into this field. Thank you.
Thank you very much, Rodrigo. Thank you very much. So it's a nice overview. Super great that you can really already implement online monitoring at every stage. So not only the traditional, let's check the piece when it's already done, but let's try to control before so that we can go much faster. Is there someone in the room who wants to comment? Otherwise, I can ask Rodrigo to maybe ask in this supply chain now that you see here, what can they do for you more like precisely, or in optics side? Do you need anything that is particularly need for you now?
Well, as I mentioned, I think one of the requirements is to adapt the production systems to the infrared band for introducing these monitoring tools into there. And then we collaborate with many of these of the people present in this room in several projects. But of course, some of the manufacturers of machines would need to give a chance to our cameras in order to develop monitoring and control solutions based in our technology, and not in the classical systems like visible cameras or pyrometers.
Okay, then I know that Jan Hendrik has a question. So please, you can unmute yourself. Yeah.
I mean, the question was more towards Andrea and maybe also to the other parts of the audience. One of the things that I'm really interested in was the question of material properties, defectivity monitoring, defectivity metrology versus dimensional metrology. Do you have any ideas of what is more important for the kind of processes that you are running?
One thing I can say is that with our cameras, they have also been used for laser beam welding process quality assurance in order to detect defects in real time by monitoring the dynamics of the melt pool. And for that, you need a high-speed camera. You need to monitor the melt pool dynamics with more than kilohertz sampling rate. And from there, you can extract a lot of information related with defects. Of course, with our tools, you can make maps when you are manufacturing the part, when you are doing the process, and you can link this data indeed to defects happening during the process. Also, if you analyze the cooling rate, this can also be related with cracks or tensions, stress happening during the cooling down of the part. So it can help you to improve the process.
Yeah. So what would be the resolution limits that you actually have?
In the case of laser welding, where we have made this test, we have measured defects of between 100 and 200 microns, or something like that.
And the question is this enough? Is the resolution that for the, well, of course, Rodrigo offers it for laser welding. So is there someone in the room who wants to comment about, do you think it's enough for 3D printing setup, or there are some extra needs?
I think for optics, it would not be good enough. Yeah.
Okay, so Yves, I see you want also to say something.
The same possibly holds for LBM, laser beam melting. So defects are there, more likely a little bit smaller. But anyhow, I mean, it's worth a try. It's worth a shot, and to figure out if that brings any other valuable information. It's not only about defects like pores, but it's also about the heat history of your part, which drastically has an influence on your microstructure. So I think it's still a really valid approach. And so Rodrigo, I would love to contact you after this meeting, so and chat a little bit about the possibilities.
Magic word, he was told. After how much? 45 minutes is already too long. We never heard this word before. Please, let's stay in contact. So let's not forget, this is the idea behind this meeting. So thank you, Yves, for already mentioning the interest with Rodrigo. So as we said, you can connect offline and we can help you with this, Jose and I. So please keep this always in mind. So also, before maybe I give you the word again back, I would like to say a little bit of advertisement about our European funded project, Multiple, that is actually also aiming in this case, in hyperspectral imaging snapshot devices. And I know we are really, really fond in testing our devices for 3D printing and for all these facility and mechanical facilities where is needed to have an online control. So I know that we will be present at Siemens, so this event that already Jose mentioned. So please keep in mind, if you want a device that is also fast and reliable, and maybe, well, I cannot promise on the resolution, but I will talk about it with my colleagues and see what we can do so that we come to Siemens very prepared to answer your questions for 3D printing. But now let's maybe leave the floor to Yves, that he will tell us better what he needs, what we can do for him. And please, the floor is yours.
All right, thank you. Let me try to share the screen real quick. Just tell me if you see. Can you see my screen? Full screen? Yes. Are we happy?
Not yet. Yes, exactly.
Awesome. Okay. Well, thank you for giving me that opportunity. I will also talk a little bit about progress and current challenges in laser beam melting. And one of these challenges is process monitoring and process control. So this fits perfectly into what Rodrigo said beforehand. So first off, for those who don't know us, Econity 3D, we are a provider of machines, but we basically want to provide one-stop shopping for customers. Means it all starts with consulting, because we've heard that beforehand from Andrea also, and also Onno. Consulting is a big issue because the technology itself is quite new, right? So we also offer job shop if customers just want printed, easy parts. That also enables us to provide material distributions. But our main topic is testing facilities in which we provide feasibility studies for our customers in order to make sure that new material classes can also be processed. And once that is proven, we provide the customers with machines for their initial individual application. So here are some of our machines, starting with our largest machine on the left-hand side, the Econity 1, which is a 4-laser production system. Then on the bottom, we see the Econity MIDI Plus, our newest development, also towards multi-material, multi-metal LBM processes. On the upper right-hand side, the Econity MIDI, which is a flexible system for advanced research and development, but also due to the possibility to extract the process chamber, can be used for efficient parallelized setup times and therefore reduce cost for production in a serial application. On the bottom right-hand side is our entry-level system, which is meant to do fast material studies and basically find out new material classes there. So now let's talk maybe a little bit about some applications which you can provide with our systems, because they are highly flexible, and you as customer can basically, like Lego, put together your system like your application needs it to be. So one application could be micro SLM. That's something which Fraunhofer ILT did also together with our machines. Here, just an example of nitinol, which is a shape memory alloy, which can be printed on the right-hand side in such stand. And yeah, the challenge there was building fine structure. So what we see on the right-hand side is those walls have a structure size of 32 microns, which is yeah, pretty small and smaller than the standard of additive manufacturing, I would argue. So that is possible by just changing the machine setup, so to say. Another example is just exchanging the laser source itself. So there are certain materials such as pure copper, which don't really absorb the infrared laser light, which is taken by standard quite well. So what you do, you just exchange the laser source, of course, also the optical coating. You all know, yeah, you all done your homework about optics. So once you've done that, you can actually process this completely new material, or not new material, but new for additive manufacturing material, pure copper, which is of course really interesting for electronics. So next example here is high temperature preheating, which basically can enable you to process materials such as titanium aluminides, which are really prone to crack formation. And we see a little demonstrating object here on the bottom right hand side. So enables this micro welding process for also non-weldable materials. Another example, and yeah, we are particularly proud of that, is a collaboration between us, Econity 3D, and Aerosint. They have developed a multi-material powder deposition unit, so to say. So we have integrated that into our Econity MIDI Plus system, and we are now capable of actually building parts which consist out of 2 different materials. And of course, this opens up a whole new research market and also industrial application market. So you can imagine processing one material is difficult enough sometimes, but now making sure that the interaction zone between those 2 materials is good for the use business case, yeah, is the next challenge, so to say. So we offer that tool for customers who basically, yeah, want to play around with that, want to figure out if they can make their material combination work. Last but not least, and most likely my favorite topic, is process monitoring. Yeah, we were asked not to show any videos here. So what we have is also an inline high-speed imaging process. So that allows us to take a look at our process itself. So it's coaxial. We see here the first laser spot. It's a pulse process we have shoot here. Then we see the involvement of the melt pool. And so what you can do with that powerful tool, you can actually get an idea of what's happening, because typically the process is really, really fast and you don't really see a lot on what's happening. So once you get the possibility to see all that, you can basically change basic parameters like modulation frequency and the modulation length. And what you see here, that's the contour scan. Here's a laser again. The evolving melt pool is a lot smaller here than on the bottom or on the top. So that allows you to do fast material changes, fast material development. However, all that is manual. There's no automated control, because that is all really, really, really fast. You have several meters per second your scan head moves. So if you want to do any inline process control, you need to bypass your software. And that's basically what we have done in our last slide. And then I'm done with the different sensors. So on the right hand side, we see the sensor signal. So we see a little bridge, which in additive is not easy to manufacture, because you would want to support such structures. If you don't do that, you can get those defects as you see here. So on the top, we see our non-control process, also the sensor signal. You actually see the defects. And what we have done is we applied an inline process control to that. So once we've done that, we see the quality of our part is tremendously increased. However, the issue here is all those control parameters largely depend on the material you apply, on the powder fraction, and yeah, the whole setup you use. So that is done for one material now, but believe me, next day a customer calls you and says, well, what's up with my material in question? So that's also a tool set we are currently developing in order to hand out to our customers to develop their own ideal parameter sets for their individual materials. in order, to have like this industrial process of additive manufacturing. Well, and that's all from my side. If you have any questions, just tell me. And
thank you very much from the beautiful city of Aachen. We have the company Cognitive 3D. It is great to have a company. We have actually a question all the way from Jena. Eric, what's your question?
Yes, Yves, thank you for a very impressive talk. I was in particular thrilled by the multi-material thing. Is it really a powder bed technology with two different types of powders?
yes, absolutely. And that's what Aeosin has developed. They also own the IP on all of that, and they can actually pattern two different materials in X and Y and also in Z. So what we have done together with Aeosin now, we have synced the patterning signal with our laser signal. So that was needed in order to make sure that copper, in that case, has different processing parameters than steel. So that is truly two different materials. However, it's a brand new technology. So Aeosin is also quite a young company from Belgium. So if you are interested in any other materials, you might need to figure out, can that material be deposited? There are certain limitations. And then, of course, can it be processed with laser beam melting? Because if you have, let's say, iron and aluminum, you might form a thermate which doesn't really interact really well. So you might want to talk about a gradient and stuff like that. But all that, in theory at least, is possible.
Okay.
We have another question all the way from Graz, Joanneum.
Thank you. I have a question because when I was looking for some information on internet and came across your system, I saw that you can install multiple lasers, and also there was some information that you could simultaneously and synchronously move these lasers, one in front of each other, one after each other, and then enable some interesting things. Can you say a little bit more about that?
Sure, and sorry that I didn't put that in our slide. It's difficult in 6 minutes show everything which we do. So our multi-laser processes or systems are always full overlap. So for one, that is really important for increased productivity, because otherwise, you don't have 4 lasers working on one part, basically. But on the other hand, that enables us to do exactly what you said. We have synced our lasers to each other, and so we can dictate the lasers to go in front or after the other laser. So I think, no, I don't have the slide here. So within our software, you can basically, for each part, choose, is that the master laser, is that the slave scanner? And once you've chosen slave, instead of choosing a scan speed, you get to choose a time delay, either minus when you want to go in front or plus when you go negative or after your primarily master laser. Also, what you can introduce is wobbling. So you can actually have your second laser go behind in a sinus or, I don't know, an 8, because you get to wobble in X and Y. And you can also do that with 4 lasers. So you can do all kinds of crazy stuff, basically.
Excellent. One question from the YouTube universe. Hello, YouTubers. I have a question from Sander Gillen from NTS of Tel. He's wondering that at some point during the presentation, you were pointing towards real-time optical feedback to make the next step. And he wonders, what would you need to accomplish?
What we need to accomplish? Currently, we all do that because you need to be extra fast. You need to bypass your control software, right? And therefore, what we are currently looking for, all that is done with an FPGA. So I told about, we have found control values for steel, but the control values for aluminum might be different. So what we are currently lacking is a chance to enable the customer to play around with different control values within our software, which is web-based, and have that put to the FPGA. So that's what we are lacking in terms of technological approach, so to say.
Thank you very much, Yves, for a great presentation. You know, Aachen is now, I think, second 2 of the cities in Europe with most members. I want one more, a Cognitive 3D over here. I hope that we can make this happen very, very soon. And we go to the next speaker. We go to OEB. Thank you very much, Manuel Bertani, for being with us this afternoon from your beautiful office full of sun with a fantastic webcam equipment. The floor and the attention of everyone is yours.
Thanks. Good afternoon, everyone. And share the screen. Okay. Do you see? Okay. I'm Manuel Bertani, and I'm an application engineer in OAB and IMT. OAB is a company that has 40 years of experience in high precision machining for the sectors like motorsport, aerospace, and medical. IMT is an innovative additive manufacturing startup created by OAB. Our production cycle starts from the selection of the material, and we can also provide the customer support in the design for additive manufacturing. And let's study the optimal orientation for the parts, and we can create the superstructure that are necessary for the DMLS process. And after the design phase, we can manufacture the components in our machines according to the material and sintering parameters chosen, and which we are able to develop according to the customer requests. And after the construction, we treat the building platform with the parts in our furnaces, and we are able to carry out many types of treatment, including stress relief, quenching, tempering, solubilization and aging. And we are also available to develop customized treatments according to the specification of our customers. The additive manufacturing and heat treatment process are constantly controlled through mechanical characterization and metallurgical analysis that are carried out in our laboratories. After that, we do the CNC machining. We often do this machining, and OAB is able to carry out 5-axis milling, turning, and ADM machining on very complex parts and with very close tolerance, such as a Formula One part. And each piece made is checked to make sure that all the customer requests are respected. And only when we are sure of that, the part is delivered to the customer, often with the quality documentation. Next, for the design phase, we use some CAD software like Cimatron and other softwares, while for the realization of supports, we principally use the software materialized images. And as the MLS machine, we own 3 EOS M2290 with mono laser and the 8 platform, and a Concept M2 using with dual laser. For the treatment, we have 3 furnaces that operate in an inert atmosphere and can reach over 1000 degrees. In our laboratories, we can make tensile test, hardness and density test, and also the metallurgical analysis over the additive manufacturing material. OAB always owns several 5-axis milling automated machine to work the additive manufacturing parts, and owns some tuning milling multi-axis centers and the CNC tuning center. And for the quality control, we have the latest generation of Zeiss CMM machines. We have a Zeiss 3D scanner, and an ultrasonic thickness gauge, and we can make the other classical control like roughness, manual dimension control, profiles, and so others. The advantages of our company are to be a single partner for all the processes related to the production of an additive manufacturing component. And this involves high efficiency and the reduction of lead times, because all the operations are internal in our industries. And thanks to our technologies and our machinery, we are able to create complex parts for very demanding sectors like Formula One, motorsport, aerospace, medical sector. And our goals is to produce quality components. And in this sense, our company has several certifications, both for aerospace and also for the medical sector. The future developments that we are interested in and in collaborate with other companies are the development of an automation of the additive process. We think it is important to improve the safety and the lead time. Also, we are searching for an integrated solution for CAD, support design, and simulation of the additive manufacturing process that is able to manage all the files like STEP and STL in a single software suite. We think this is very important. And also, I think it's important the development of the hardware and software for the automatic control during the DMLS process. I saw a very good presentation about that, and so it is all for us. If you have some question, some questions, write emails or call us at this our contact.
Very good, Manuel. Thank you very much for your talk. So, as you maybe don't know, because you're also a very fresh newbie of EPIC meetings, I can maybe focus on your last mentioning of you heard an interesting talk. So that means that you can mention what the audience can do for you. So were you addressing maybe an IT, or what was your direct question? So of an interesting talk, and maybe you want to talk further about it with the speaker.
Yes, we are searching for collaboration for that topic of the automation of the AM process, because we think that it's important when you move the building platform, when you have to work with powders. It's very important that to do with automated machine and not for manual handling. And so we think it's very important also the inline quality control, because for us, it's very expensive every job to monitor with microstructure, tensile test, the additive manufacturing process. So we think that in the future, with online monitoring, online quality control, we can do this. If we have a good quality control online monitoring, we can, after the printing process, we can say, okay, the part is good, and so we can go with the other working, machining, surface finishing, quality control, and other things. And also a software that is a single software for the additive manufacturing, because now you have to have one software to topology optimization, one software for design, one software for create the supports, one software to go the files to the machine. And so we think that for a productive company, because we don't do research, we produce part for other companies that send us the files and send us some pieces to make. We think that it is very important to us to improve our business.
Very good, Manuel. I guess you really made now a shopping list. So if someone wants to comment on this, we can speak about it already now. Otherwise, it's recorded, it's printed in our mind, and there is Manuel name and contact there. Otherwise, you can ask us if you want to propose something to Manuel. You're really welcome. So now I just take maybe the opportunity to introduce 3D&T. So Fabio, you have the camera off, but I know you are there. So maybe you want to introduce your company.
Sure.
Yeah, there you are.
Here I am. Now, well, it's just this invitation came last minute, so I didn't have any presentation ready for you so far. Thing is, we are a startup company that started basically a couple of years ago, developing innovative 3D printing systems, SLM systems. And we are not so far disclosing our products or just a bit of it, because it's our strategy not to do that as long as the products are not 110% ready. So we are now close to this phase, and so stay online. And
so you're listening more than talking, I see. That's a good point. Then if you have then to ask someone offline, then of course you can always support you, but good to know we have a good listener there. So now maybe Jose has a question.
Yes, of course I don't. I have a question from the YouTube universe. That's what I do here, to be a YouTuber. So I have a question again from NTS Optel, all the way in Nijmegen, a really, really cool company. A question for Yves. Would you opt for different workstations for different steps like printing and inspection, which may have impact on accuracy, or rather have the single station, which is of course more expensive?
We have some station for the design and for the support structure generation, but I think that one software suite for all the processes is very good, because you don't have to send files from a program to another, and you have only one station to do all the things.
Manuel, you and all the rest, I want to ask you a favor. After this meeting, I'm going to make many introductions, because many people are asking me to introduce to each other. All I ask you is you follow up with every introduction I make. That's very, very important. That's what drives Epic. Please follow up with all the emails. Back to Francesca.
Very good. So if I don't see any other question, maybe we keep going. So then maybe we only have time later for further questions. So now is the time of Christian. So Vanguard Automation. Welcome. Thank you for joining us today. Still quiet so far, so the floor is yours now.
All right, good. Can you see my screen?
Yes, all perfect. Thank you.
I should move you guys out of the way. Okay, good. All right, yeah. So my name is Christian Koos, and I'm CTO of Vanguard Automation. Vanguard Automation is in the southwest corner of Germany, and we're doing tiny things. We're doing 3D lithography tools and also processes for applications in the field of photonic integration. So photonic integration, what is this about? Well, it's about many tiny devices that you can fabricate on chip and wafer level. What you see here in the background is an 8 or 12-inch silicon photonic wafer, and such a wafer can carry 10,000, 20,000, 30,000 devices. The devices are very small, apparently. They rely on very tiny waveguides. You can see here the basic building block of these structures. It's a silicon waveguide with a high refractive index surrounded by a low index silicon dioxide cladding. So why am I showing this? The key challenge in photonic integration is to get light into these waveguides, because they are very small, sub-micrometer cross-section. So you have to align these chips with very high precision to some optical fibers or to some external lenses. And that's a challenge, which makes the whole thing difficult and expensive, and that's something that we are overcoming by using 3D printing. So what you see here is what we call a photonic wire bond. A photonic wire bond is a 3D printed polymer structure. It's fabricated by multiphoton lithography in a liquid photoresist. And the good thing here is that you can directly print it, and you can very nicely align it to on-chip structures. What you see here, this is a silicon waveguide. This is basically the guy on the upper right-hand side, that thing. That's another silicon photonic waveguide, and in between, we can print that 3D structure, and we can align it to the on-chip coupling interface, and any inaccuracy of the placement of these chips can be compensated by the 3D shape of that beast. So that means this structure is calculated on the fly during the printing process. So this is a very versatile technology. We can use that to build up complex, what we call photonic multi-chip modules. These are simply modules that consist of different chips, for example, indium phosphide lasers, silicon photonics, light sources, integrated filter chips, and you can go from a laser, for example, to a silicon photonic chip with one of these wire bonds. You can see one that is now going up, and it's going back into the on-chip, into the plane of the on-chip waveguides. So that's, you can also connect like surface emitting chips to edge emitting ones. We can go from one chip to another. Here you can nicely see that this photonic wire bond here is taking a small bend to compensate for an alignment inaccuracy of the chips. So that's something that we can overcome here. And we can go from planar waveguides to non-planar structures like this optical fiber. That's a multi-core fiber MCF with 4 fiber cores. You can nicely print, connect an array of in-plane waveguides to such a structure. You can also see that here we can taper up the diameter of this optical waveguide that goes to the fiber. So we can really use the full 3D structurability of these waveguides to get high coupling efficiency. Yeah, so obviously the advantages are that with this technique, we don't have to precisely align the chips. We can connect 2 chips with completely different mode field profiles. On that side, we have sub-micrometer mode fields on the silicon waveguides. Here we have 10 micrometer mode fields in optical fibers, and we can fully automate that process. Yeah. We can also use our tools to print other microstructures, for example, lenses. You can see here a gallery of different lenses that we can print on chip or on wafer level with very high alignment precision to the facets of optical lasers. So what you see here is a laser standing upright, and onto the facet we can print a lens which, for example, focuses the beam or which collimates it. We can have a structure with a 45-degree mirror. That's the top view here. So here we have a mirror which is curved and which redirects the beam from an in-plane to an out-of-plane direction. We can have fiber arrays with high numerical aperture lenses. We can have more complicated structures like these turning mirrors or multi-lens assemblies where we can have diverging and converging lenses to collimate beams that come out of fibers or of tiny structures. So that's a very versatile approach that we take here. The tools that we are selling are geared towards industrial production. What you see here is a process chain of 3 tools. The first is a dispenser. So that piece basically dispenses small amounts of liquid photoresist onto chips or onto wafers. The second is our 2-photon lithography system. That defines the 3D structure. With that, we print in this liquid resist. And the last one is then for developing. That means everything that's not exposed is just washed away. And we could have further units here to apply overcladding to the chips or to the waveguides or to the lenses that we print. Yeah. That's something that we do in cooperation with Ficontech. So Ficontech is building these machines for us. Ficontech is a leader in photonic assembly and testing equipment. Yeah. And what you can see here is our 3D lithography tool, the Vanguard Sonata 1000, we call it. It's a pretty sturdy system. You can see it here. It's built from a granite frame, so it's really able to sit somewhere and to print these waveguides with sub-micrometer precision in a normal environment, so you don't need any special vibration isolation. And importantly, that whole thing comes with the processes and the software you need for doing that. What you see on the upper right-hand side is image recognition. Is an image recognition tool with which you can find the coupling interfaces on our optical chips with an accuracy of better than 100 nanometers. And from this information on where the waveguide has to start and to end, you can calculate the full 3D trajectory on the fly. That's done by our software, which is called Brightwire 3D. Yeah, so that's as a short overview on what we do in printing very tiny sub-micrometer structure in the field of integrated optics. If you have more questions, drop me an email or contact me after the meeting, or let's just discuss now. Thanks.
Fantastic, Christian. We know each other for a long time. I was one of the ones who touched that machine first. So he told me, the machine is ready, and I took my car and I went to Karlsruhe, and I actually was one of the ones who saw it running for the first time. True. Congratulations on all the things that you are doing. You are not a newbie at this EPIC meeting, so you know the EPIC question. What can you do for them? What can they do for you?
Okay, good. Well, then that's what we can do. I think is obvious. We can provide equipment processes for printing of small polymer parts, micro parts, nano parts on chips and wafer level, and we can do this all the way from research. So some of our machines are going indeed to research labs to production. So this full scale we can cover, and we do not only sell the machines, we also develop the processes. So the customers that come to us, they have a certain structure in mind that they want to have printed, and we have the expertise to then develop the process together with the customer and sell a machine with a process that is guaranteed to work. So that's what we can do. Second part of the question is what other people can do for us, right? Well, I mean, we are building these systems, but our focus is indeed on building the system and developing the processes. It's not on the optical components. So we do build our hardware ourselves at the moment where we have to, but that's nothing that we have to do necessarily. So if someone else can support us here, can help us here, can provide special parts, beam scanners, optical modules, pieces of software. We are completely open to discuss. The field we are covering is so widespread, so it's impossible that we as a small company can cover all of that. So we are extremely open for cooperations here.
And there are going to be a lot of cooperations, but I'm very interested on the market side first, because you are opening the door for the 3D printing of optics and micro optics. You were the first of a few presentations and discussion also with multiphoton that we're going to have. But I want to talk to Onno, because Onno knows the market very well. There's many companies in Europe on 3D printing of optics who are doing very well, like Lux Excel. Onno, have you seen the 3D printing of micro optics that Vanguard and later Nanoscribe multiphoton can do? And how do you think the market is developing towards making ultra precision nanometer shape, nanometer size 3D printed structures?
When I look at their capabilities, I think they are really unique and advanced. Of course, you see a lot of these developments coming up, but I must say that when I look at this presentation, I think they're really on the top level of this development. And the other aspect I think also is that when you look at the production, that's one side, but an interesting element of this technology I think is also when you look at the printing process setup and the simulation of the process, because with such precision you can make far more intelligent decisions about how to build your print strategy and how to overcome some obstacles that we now see in printing really tightly fit near-net shape structures. So I think this is really a development that everyone should really look for.
It's the biggest thing that has happened since I work in optics. The majority of the companies doing customization of micro optics manufacturing, and the world is their oyster. The potential they have for growing, and that's my personal opinion, is huge. I've never been so excited in my life as micro optics in Europe developing. But Christian, I have a question from the chat, from the YouTube universe. They are wondering about reliability of your photonic integrated circuit packaging structures.
Yeah. I know this question very well because I often get it. We have, of course, tested this. So we have done tests. So in integrated optics, telecommunications is a very important field. There are standard tests where people test structures for thousands of hours at 85 degrees centigrade, 85% humidity. And that's something that we also did with our structures. And the structures that we built in our lab can pass all relevant reliability tests, which does not mean if we engage in a customer project, we repeat these tests always over and over again, because the reliability is not just the structure that we do and the stuff we put on top. So we overclad these waveguides to protect them. It's also in the assembly that we get from the customer. So if you want to be really sure, we have to run a demonstration project, build up a few prototypes, and then torture those until they die and see how long they live. But yeah.
There's a few companies in Europe that started working in similar technologies. I have a question in the chat, and I know Vanguard can do it, but I want to ask Ruth from Multiphoton. I have a question in the chat for Mr. Alansi. He's wondering, can you print 3D photonic crystals?
That is a question for me?
Yes.
And I've seen that you unmuted the mic.
Of course.
Yes, we can, of course. We did that, we started that, back in 2003 to 2006. So we had many projects and photonics crystals and also materials for photonic crystals, and did all the works up and down. So that is one part of the works actually we do. But I would not like to tell you more about that, because this is a very old historic thing we did, and we just keep it going.
For those of you who don't know Multiphoton, you could tell us in short what is Multiphoton and what can you do for them and what can they do for you?
So for about 20 years now, we are doing that kind of technology in printing micro-optics, printing waveguides, on printed circuit boards, on wafer scale, and so on. And what we do is we are a hardware supplier, a service supplier, and we also do production with some of our clients. So there is one dominant production actually with Nanoplus, in a supplier of IR lasers. And how far, when it comes to reliability, that was one question. we are now beyond 10,000 hours testing of the devices in the test environment the customer is using. So I'm actually very curious about the materials Vanguard is using. So that is one question I would like to give back, because so now that you unmuted me, you have to live with it.
Yeah. Well, all I can say is that they work. So sorry, I can't go into any further detail here.
Let me introduce you, Ruth and Christian, to a friend of mine. The meeting started very Italian. Now it's moving towards something a little bit German. Klaus from Genoptic, thank you very much for joining us. Why did you join this meeting? And do you have some question or comments about two-photon polymerization presented by Vanguard and multiphoton?
Yes, thank you for your introduction. We are coming from a little bit other side of the story here. We are a technology company, and that means we are producing less or more components for additive manufacturing. We don't use additive manufacturing up to now. But within this case, it was quite interesting for me to hear this presentation from Christian, because maybe we can come into contact with respect to special coatings, to producing special micro-optics, also simulating small optical systems, which could be a component which can be used in its machine. We are just now we are working in this field of integrated photonics just now with test systems, not so much with components for these 3D printing systems here.
You know, before the meeting, I make a matrix with the companies that I want to introduce. I'm wanting to introduce Klaus to Vanguard, Multiphoton, and Nanoscribe. So I'm going to make this introduction offline. But thank you very much for being here. I'm going to stay in Germany, but I go to one of the most beautiful cities in Germany, Heidelberg. If you ever had the chance to go to Heidelberg, being in the city and look at the mountain, it's just beautiful. But you also make fantastic micro-optics. This is not additive manufacturing. This is subtractive manufacturing, but perhaps the most cool manufacturing process that I know for micro-optics. Heidelberg Instruments, thank you very much for being with us. The floor and the attention of everyone is yours.
Hello, good afternoon to everyone, and thank you for the nice introduction, Jose. So you were supposed to be here last week, I think, and unfortunately it was not possible due to the crisis. So next week we're going to meet at the same time, also through video. So I'm going to share my presentation now. Can you see it? Okay. So I'm going to talk about how to create complex 2.5D structures in thick positive photoresist by direct laser writing. So this is the principle of grayscale lithography. So as Jose mentioned, it's a subtractive manufacturing process. So instead of building structures by adding up elements of whatever material, here we are exposing some photoresists, and when they have been exposed, after a development process, what has been exposed is removed. So by controlling the dose and the intensity of the laser beam that is focused onto this layer of photoresist, we can remove more or less photoresist and build 2.5D structures. So Heidelberg Instruments, we are a world leader in the production of innovative maskless aligners and laser lithography system. So maskless aligners is because we have a range of product that is competing with the mask aligners. So I would not recommend you to go maskless in the real world now, especially in public transport, but in lithography, it's recommended because it's fast and flexible. So one of our best working series for grayscale lithography is the DWL series. And so it is a pattern generator for mask making. So for people who are still using masks, for example, with a stepper, and also can do some direct writing onto wafers, for example. And it's a perfect tool for grayscale lithography. So for those who are not familiar with this, the principle of grayscale lithography is we use UV exposure with specially modulated light intensity. So here we have a low dose of a laser light. And then here we have a higher dose of laser light. And with this dose, we can expose more or less deep of the photoresist. And then after development, we have this gradient of intensity that is transferred into the photoresist topography. So here we have a positive photoresist, and the thickness that we are working on is like basically between 0 to about 100 micron. And it's resting on a flat substrate that is typically a wafer or glass sample. And afterward, the resist topography can be transferred to a different material by etching. So we can etch the wafer or the glass underneath the photoresist, or by molding, like with electroforming, or by molding with the Onno stem, for example. So how does it work? Like when we go from one idea to a working structure in photoresist. So we first need to have to use a CAD software to create the design. So it could be like a real 3D structure in STL form, for example. And then we need to introduce this STL shape. For example, here we start with 2 hexagons, with 2 cones cut into hexagonal shape. And then with our software, we can step and repeat it into a large array. And then this software can convert it into data that is understood by our machine. And our machine principle is working with a SLM, a spatial light modulator. So in the case of the DWL series, it's one acousto-optic modulator. And we have a way also to scan this beam with an acousto-optic deflector. Then we have a mirror and some focusing optic onto the substrate. And then the substrate is resting on a XY stage that is moving along the Y-axis, while the scanner is scanned, the AOD, so the acousto-optic deflector, scans the beam in the X direction. So we can write the structures stripe after stripe. And so the high convert 3D software creates the machine data, and it allows for arraying, stepping, rotating, and merging also multiple designs. And this software can work with different type of designs, so STL, like a pure 3D structure, but also bitmap. So for example, like a grayscale image where the white would be the deepest structure and the black, the surface of the photoresist. And it can work also with raw file, because we can work with more than 8-bit, because the typical bitmap grayscale is working with 8-bit, so 256 levels, but because our machine is using up to 1,000 gray levels, so we have to use raw file in this case. It can work also with DXF, where the layer is defining the depths of the structure. And so it's pretty easy to use. And when we are ready with the design part and the conversion, then we can just place the substrate onto the stage. So that's what the user is doing. Actually, what is underlined here is what the user has to do, and the rest is done automatically by the machine. So the user places the substrate onto the stage, choose a few parameters for the exposure, like the energy, the focus position, and then starts the exposure. The machine can find automatically the center of the substrate or align to some pre-existing structures. And then the exposure starts. Like I said before, the spatial light modulator is acting like a dynamic mask and can do like modulation of the light intensity in a very fast manner. Like we can change, like for example, from 0 to 1 in a few nanoseconds. And then we can use up to 1,000 gray levels that are accessible for each pixel. And the pixel is basically the positioning of the beam, and this minimum position that we have for the dose, like a change of dose, is into a 50 nanometer grid. So the SLM combined with focusing optic and the XY stage enables fast writing of high resolution over large areas. And when I'm talking about large areas, we have systems that are writing mask or or grayscale mask up to 1.4 meter in one dimension. So this is not typical for R&D research, but this is for industrials. And then when the exposure is done, then the user removes the substrate and then develops it, and then can inspect the surface of the photoresist. So here are some typical applications, some complex convex lenses. So here the scale is, I don't have the scale here, but I think the dimension of the central lens is probably around 120 micron. Here we have some tilted micro lenses. Here one optical diffusers. So it looks like random lenses, but actually it's not random. Here we have some diffractive optical elements where the square is probably about a micron in the size. Some Fresnel lenses. And we can also do some kind of decorative printing, where here we have like a Ganesha, one Indian god that is printed, that has a 3D effect, but actually the depth of the structure is like 5 micron. So it can be used like in printing industry, like to print like fancy and decorative elements. It can be also used for security and this kind of application. So because you asked me to have only 3 slides, so I have only 3 slides. So it's a very short version of the presentation I had last year in Switzerland. So it's like very compact. So if you have some question, I would be happy to answer them now or later.
Thank you very much, Dominique, for your talk. So 3 slides, exactly, and you didn't answer, you didn't propose the typical EPIC question. So that was a good trick, so you can have the time now. So what can they do for you, so this audience? So what can you do for them? Maybe we skip it, but what is the room for collaboration here?
Actually, what I would really like is, because I've been doing this kind of 3D structures in photoresist for a long time, but I have really seldom seen what is done after, like for example, like etching onto a wafer or etching glass or even molding. I have only seen a few examples, but usually our customers are really secret about this. So if someone could show me this kind of process, like that I could really do it, maybe do it with them or witness it, that would be really great.
Oh, that's a good point. So this is definitely so, like a service that you learn from them. So this is like a pilot line spirit.
Yeah. What is done after our machine has been doing its work, basically.
Great. So if nobody wants to comment here, anyway, we can do talk about this offline, and for sure we can in the EPIC. There's, you know, now said that a like, okay, so that I interpreted it as Klaus. Do you want to comment on this?
Yes, just one question. I think it's a really interesting technology because you can also generate a structured light field for applications. But the question at the end is there any experience on the maximum optical load which can be put on these kind of lenses? Also how many power, how many power do they withstand at the end?
Yeah, actually, it's a good question, and I would not be able to answer it because if the lens has to be used, I think, in the photoresist directly, I guess the load is probably not very high. I mean, it probably depends on the material. This I don't know exactly, but what our customers usually do, like I said, they are replicating this structure. So by etching, they etch glass, and then they use the lenses in the glass, or they are molding it using, like, for example, like some kind of homocomp material, like homocere. So this will I don't know exactly what kind of load it can withhold, but for example, glass would be a good material to use high power.
Very good. So thank you for this answer. And then I guess we go back to our agenda, and I guess it's Nanoscribe time. So, and of course, I want to say in the meanwhile, while Alexander prepares the slides, that of course is Italy and Germany. Jose, What else? If Francesca is there, is a German-Italian meeting, plus some Spanish. And then there is also Amires. We come back later to Amires. But now let's give the floor to Nanoscribe. So you are muted, Alexander?
Yes, now
Very
I'm
good.
unmuted. So let's go ahead and let's share the screen. And sorry, can you see me?
No, we don't see you, but we see the slides. That's the most important part. So very good.
Okay, wonderful. So if you see the right screen, so that's wonderful. Nice to see. I just was a bit confused about.
No, it's the right one. No worries.
Wonderful. Okay. So then, thank you for hosting me, and thank you for the lovely introduction. And so very nice to be here. Great format. I'm honored to be part of this. And so then, to myself and to the company, my name is Alexander Legant, and I have been working for the company Nanoscribe for 9.5 years. I'm sales manager for Europe, Middle East, and Africa. And today I will speak about the company Nanoscribe and its abilities in high precision 3D printing and research, prototyping, and production. And so let's just say some of the epic questions. Nanoscribe, what do we do? And Nanoscribe, what do we offer? And to the company Nanoscribe, it's a machine manufacturer of 3D microfabrication systems for production of structures measured in micrometer. And Nanoscribe stands for best results of matched hardware, software, printing materials, application-specific solutions, and exceptional customer support. We follow a holistic approach, not only covering the aspects of systems engineering, but providing complete solutions for our customers comprising the Photonic Professional GT2, for example. And this is our flagship for high precision additive manufacturing, meanwhile in its third generation. It has become a standard both for academic and as well as industrial R&D labs. This mature turnkey microfabrication system and most precise 3D printer worldwide includes easy and intuitive workflow, matching resins, a software suite, optimized process recipes, technical training and support, and an online database. And the Quantum X system. So this is our newest tool for industries requiring high precision masters for mass manufacturing based on nano-imprint lithography or injection molding. And it is the winner of 2019's Laser Innovation Award and the world's first 2-photon grayscale lithography system. So again, another epic question. So Nanoscribe, what do we do? And just to have a look at this slide, so we sold more than 200 systems worldwide, and many customers have placed follow-up orders. Please contact me for reference if you would like to know if there's someone, around, sorry, a bit too fast, someone around, your area. Due to our global service team on 3 continents with more than 12 years of experience in 3D microfabrication, you can reach us nearly around the clock. So that means on work days, 22 hours out of 24 hours. And now finally, so obviously it was a bit in a hurry, this picture. So it wanted to be shown a little bit earlier. So one of these mentioned sites is this brand new building that you see over here. And we moved into it at the beginning of the year. So everything was ready to host the epic meeting on advanced micro-optics on May the 7th and the 8th. And I mean, you know the situation. So, but now, nevertheless, so we look forward to welcoming you all for November the 5th and the 6th. And let's show a bit, so then something would, so we say about here, 3D printing. So here you see then the full range of dimensions and complexities possible. And for the 2D and 2.5D world, so what you see here on the bottom lines, so the epic meetings from the last weeks are still available on the YouTubes. And also my colleagues participated actively in the one for freeform optics, for example, and another one for micro optics manufacturing. And today, so we will focus here on 3D printing. And that means here, the point here on the top line. And for more information, like the related presentations, for example, from the last epic meetings, please contact me. And I will later on also show them email address to contact me to get in touch. So what is the principle behind this technique? We use a short pulse near-infrared laser to expose photoresist. And in the subsequent step, monomer is washed away and the remaining polymer can be used. Unfortunately, the 6-minute format does not offer enough time to explain 2pp in detail. So again, the same like before, please contact me afterwards if you would like to know more about the magic of two-photon polymerization. So there are a lot of different applications that are mentioned here. For example, the system provides lateral feature sizes down to 200 nanometer specs. And in publications, our customers have achieved line widths smaller than 100 nanometers. Surface roughnesses of 10 nanometer and below are common, which results in micro-optics with excellent optical quality. True 3D structuring is possible, meaning 3D objects like meshes or channels or undercuts as shown in the pictures below. And here are more 3D printing examples. And every object shown here with a diameter of 1 millimeter was printed in 5 minutes with lateral steps of 1 micrometer. And I mean, we heard already a bit about that. So as well, so with the Quantum X system, we take assembly-free manufacturing of photonic and optical components to the next level. Whether you require 3D printing on a single die, on wafer level, on optical fibers, or on laser chips. And here you see a top view of an optical chip where precise 3D printing is supported by integrated machine vision. Here the focus is not only on printing of high resolution structures, but also on position placement of the elements. The award-winning Quantum X has a feature detection alignment accuracy of approximately 100 nanometer and a true solution for optical integration. And that brings me to the next and the final epic question. So what is Nanoscribe looking for? And we are looking for people in need of precise mechanical engineering, low surface roughness below 10 nanometer, flexibility of design, high iteration rates. Remember, we speak of the world's highest resolution 3D printer here. Typical markets for us are, for example, the assembly-free photonic integration, medical engineering for endoscopy, micro-optics to manufacture a master for nickel shim. And so in case that you would like to hear more about that, please don't hesitate to contact me. Here you see my email address. And so to close with that, think big, print nano. Thank you for your attention. And do you have questions?
Thank you very much for your presentation. You answered all the epic questions in a very structured way. So fantastic on that. I have a question from the YouTube universe, a company called Icon Photonics. These guys are really fantastic because they have a process to package pixels at wafer level. So they actually print micro lenses at wafer level, but he wants to go into very high volume. So he's wondering about ramping up using Nanoscribe technology. How long does it take you to print a micro lens of a top of a pixel?
So it depends, of course, always on the quality that you need. I mean, that depends on everything. So typically, our customers who would like to get high numbers. And we have definitely several customers who use this machine already then to print, to get an output of hundreds, thousands, or of millions of parts. So typically they print here, for example, a master for micro-optics, so for microlens arrays, and then they do a replication and get a nickel shim out of that as a tool of replication then, or to get a higher number of parts out of it. Does this answer the question?
It's not my question, but
okay.
I think he was expecting like a time. And I think what we are talking here is that you saw some examples and you were talking about 5 minutes per structure. So I think a fraction of that. I think multiphoton optics, my friend Ruth wants to comment on this.
So to give a answer to that question, it depends actually on the micro lens, but considering the 5 minutes per structure with the slicing and hatching distance of 1 micron, which is by far too bad to create a lens on a VCSEL, we have demonstrated in between 1 to 5 seconds per lens, and it's in an assembly also. So wafer scale is easy because you fabricate a master and then you can just replicate that. But most of the customers, they don't want to use the let's say the wafer scale, because then they have to dice the components later. So what they would like to work on is on the entire package. And that is what we offer in like 1 to 5 seconds. Sometimes it takes 10 seconds, but with the high resolution and high quality.
Thanks a lot, Ruth. And I think that's exactly what I wanted, a fraction of the time, but you were very specific on this. You know what is one of the beautiful parts of these meetings? I'm making a lot of friends. I have friends like Ruth and like Christian and like Alex, and they're making new ones. I make James Field from Voxtel, who also has a startup called Vadiant. James, thank you very much for joining today.
Thank you. It's early here in the west coast of the US, but I enjoy waking up to the epic meetings.
The coffee tastes better with a discussion like this one. What did you learn so far, and what kind of collaborations would you like to do with these people?
Well, I think that the interest in our part is we 3D print grin optics. So we use nanocomposites to create grin structures. And so many of the optics that I see today are using surface features to create their optics. And so we use internal nanoparticles to do that. So if somebody needs to have a different type of optic so that they're not using multiple surfaces to create the image plane, grin can be a great alternative. And so if that could fit in your process, that would be great. We print about 125 millimeter lenses an hour. And we're moving on to thousands per hour, but we have various applications for LiDAR, commercial applications for micro lens arrays, and other devices. So we'd be happy to discuss what Grin could do for you.
Fantastic, James. So how can we help you making it faster? You have some challenges. I have companies like PI,
Sure.
Highlights in the room.
Sure. So for the next, the help we need is the next generation tool. We'd like to go from 100 parts an hour to thousands an hour to meet some customer needs, and also wafer scale. Making tools for wafer scale applications. We have applications to print right on the wafers with a Grin optic. So people who can help with that can contact me.
There's a guy who can help you with this, and he's a good friend of mine from Karlsruhe, PI. Rolf, how are you doing today?
Oh, I'm doing fine. Thank you very much. So it's nice to
see
meet
the
a lot of
challenge?
people again.
Oh, wait. Did you see the challenge that James has for you?
Yeah, there's always a challenge in this kind of production tooling. So what we can offer is positioning devices from the nanometer scale up to micrometer range. So it's like Ruth mentioned, it's always a question, what accuracy do you need? What velocity do you need? And so we can offer a broad range of positioning devices, starting with ball bearings, roller bearings, up to air bearings, and piezo technology can go down to the sub-nanometer range, depending on really what you need. Yeah? And the challenge is very often to combine these systems together with each other. And then we offer also solutions that we can combine a existing galvo scanner on your side with our positioning devices using a specific
to automate the manufacturing process. Remember, in November, EPIC meeting on automation for manufacturing at PI, at the building of PI in Karlsruhe. And later on next year, we go to Nanoscribe and keep going around the world. And we go to the next presentation. We go to EOS, and Matthias is here to talk to us about how the supply chain can help the manufacturing of some of the best 3D printing machines. The floor and the attention of everyone is yours.
Thank you very much, Jose. I'm really excited to speak in this fantastic round of people. And we're going from micro to macro 3D printing now. And I would like to talk about challenges and opportunities because I believe we all share some of those challenges and opportunities in this round. Okay. EOS is a world leader for 3D printing technology, especially for the additive manufacturing, additive layer manufacturing technologies. We do polymers as well as metals, and we are around since the beginning of 3D printing. We have by now more than 3,500 systems installed in the market, which is the largest base of industrial 3D printers. It spreads across 68 countries, and we have more than 1,300 people working only on 3D printing. Our challenges are moving from a prototyping market to a production market. Prototyping is now some decades ago for us, but production is something we worked on for the last decade. And new topics come up, which are, for example, quality control. So we heard something about that earlier today. It's also robustness. It's how can I differentiate myself as a supplier in this market? It's cost down, of course, automation, integration. And for all those topics, I'd say this is where we are today. We have a working solution, but let's be honest, 3D printing is still pretty far away in terms of maturity from technologies like injection molding or milling. So we have some homework to do. And for the future, I see the topic of digital factories, Industry 4.0. And well, did some of you notice that during the last weeks, there was an increased interest in production flexibility. Due to the corona crisis, we got a lot of customers telling us they need more flexibility in their production. They want to balance between different products and be quicker responding to the market demand. And I believe that we from the 3D printing world are the first ones who need to pioneer these digital factories, because our technology is inherently digital. And this is the challenge for the next years, but it's also a big opportunity. There is one other opportunity I would like to talk about, and it's about the design. And I have a historical parallel for you, which is the Bronze Age revolution. If you take a look at the picture, you see the transition around 4,000 years ago in Europe from stone to bronze. And what people did first was to make the stone tools they chipped before out of stone in bronze, same design. And it took a long time until actually the freedom of design by casting was used. You see here is a broader blade. There are some lines at the side to help mount this axe head. And then people arrived at the ideal bronze axe design for bronze casting. It's a hollow axe, and it could be mounted by just putting it at the end of a stick. But it took 1,000 years to get from the first bronze casts to fully embracing the freedom of design of bronze casting. And I see that something very similar is happening today with additive manufacturing. The picture below in the middle is a manifold, and it still reminds you a lot of a conventionally made manifold by drilling channels in a block. There's not so much innovation here. And I wonder, how long will it take us to get to design such as this, which looks more like the vascular system than it looks like a block. And I believe that there is the big opportunity. So how can we bring more functionality into products and more flexibility into tomorrow's production solutions? This is no less than a revolution in manufacturing, and it is also the dream of my company, the dream of EOS, to revolutionize the world of manufacturing. For example, here from sea anemone in nature to a sea anemone inspired design for a heat exchanger printed on an EOS machine in copper. This is just a little story, and I would like to join this vision with you, and I believe that we can work together towards this vision. The demand is created at the end users in the market, so we need to come up with great solutions for existing problems, and then we will come to work together in this group of people with very diverse technologies. I've been very impressed with your presentations, and yeah, let's go down this road together. Okay.
Thank you very much, Matthias. Thank you very much for being here. So it's nice because I guess meeting you in Wetzlar was one of my last trips. So seeing you now online is like reminding me at some point we will meet in person again. So now my question is the epic question. So Matthias also is not trained, so let's let him a bit get warm with the epic question. So what can they do for you? So let's focus on this. We know, I guess, EOS machines are well known, but what do you need from this supply chain here?
Well, I'd start again with the demand. So I've seen great presentations from Onno and from Manuel, which already help creating the demand in the market, working with customers. I believe that this is the first step. This is very important, and we can support each other there clearly. There are other manufacturing technologies in here, and still we have the same goal of developing this market. So we can do marketing together, definitely. We can tell the story, we can tell why 3D printing is great. And on the supply chain side, I mean, our machines are made of lasers, are made of optics, a little bit of mechanics and software, and we need to develop this whole 3D printing ecosystem. So I believe there's a lot of space for collaborations.
Someone of these optics and mechanics want to make a comment on this now? Or lasers, because maybe we have Daniela here in the room. Daniela from ILAS is here, so our laser supplier of the day, I would say. So if Daniela maybe wants to introduce herself and say why she joined this, you joined this meeting.
Hello to everybody. Main reason to join you is that ILAS is developing very interesting laser systems, and we are looking for application of those lasers even in that field. When I'm saying very specific lasers, I'm speaking about millijoule picosecond laser with kilohertz repetition rates. And it's infrared lasers, but we are also very advanced in harmonics generation as well.
Very good, Daniela. Thank you for this comment. So maybe Matthias, yes, you want to comment?
Yeah, I mean, infrared lasers are certainly interesting for the plastics technology. I'd love to go into some details and look at what you offer and then make connections within EOS.
Yeah, you're welcome.
Matthias got it already. I mean, he's here since just a couple of hours in Epic, and he got already the point of connection. So now maybe we can also ask Udo from Excelitas. So optics, coatings, lenses, why are you here?
Hi, everyone. So I'm Udo Kirchner, Process Development Manager at Excelitas, and Key Optic is a part of that, and has been in the industry, laser material processing, for the last like 30 years. And we are working through some other partners, I think already kind of together with EOS regarding FTETA lenses and other optical parts. And I'm here to learn what, we are very interested, or we are dedicated to different wavelengths. So starting SLM in IR. Now we are going into green, and I saw this nice picture here from a pure copper 3D printer. These is a very important and interesting information for us to see where our customers are going. We see the advantages of the green laser with for the copper processing. Less sputtering, less power, better structures and things like that. And so we are always open to for going for OEM parts for testing and things. I think it's pretty much the same like here my colleague at Yin Optic is looking for. So it's for us, it is very, very important to know where the industry goes, and like developing a new FTETA lens for a certain wavelengths, it's taking about a half to 1 year to get it in serial. And for us, it's to be on the top of the development, working very close to the manufacturers is essential for us. So what we can offer just get in touch to us and tell me what you want to do, and I will tell you if we can do it or not.
1 year is better than 1,000 years, as we said, as we heard before. So it looks promising.
Absolutely, I agree.
So I guess we had the question from PI, right? Am I wrong? Rolf, unmute. I'm prepared. Maybe we are wrong.
I'm unmuted. Thank you. No, a question from our side. Yeah, as I mentioned before, we start really from the very high precision positioning devices. So really from semiconductor industry nanometers. And if you work in metal additive manufacturing, where do you see the limitations there in structure size? So is there precision needed, and what kind of precision will there be needed for the future?
Okay, it's a good question. I'd say in terms of precision, the laser scanning devices are pretty good enough. So our melt pools on the metal side are typically in the range of 100, 150 micrometers, much bigger than the positioning accuracy and precision of laser scanners. What is very important is reproducibility, and how does that change over lifetime? Okay. And also calibration is an important topic. So yeah, that's my sum up. So we are happy with precision accuracy. Those systems need to be very, very robust, and we need smart ways to calibrate those systems.
Okay. And do you see any need for the future coming far below this 100 micron you achieve today? Is a 1 micron or even less range achievable with metals?
In general, I do see a demand for such small components. The aspiration of EOS is to make this process industrial, make it standard, make it easy. At the moment, we do not plan to get smaller, but we do some special machinery to make the spot sizes a little bit smaller for special applications. And there are also other companies who do that. I mean, we've seen the stereolithography today. There's also a company called 3D Microprint, which is located actually not so far from Jena. And they do everything we do, but 10 times smaller.
Thank you.
Getting unmuted. So last but not least in this little round, I bet Gwen from Skylabs wants also to tell Matthias a bit what they do. Am I correct?
Yes, hi. Very nice to be with you again today. Thank you, Francesca. So I'm Gwen from Skylabs. We are a beam shaping company working in laser material processing. And we actually do work with multi-kilowatt high power lasers, which are suitable to additive manufacturing. If I have, once again, I just want to say that regarding the classical EPIC question, on our side in this area, we are looking for machine manufacturers. We know that there are actually needs for beam shaping with end users, but we have to work with the machine manufacturers for that. So if I can get in touch with you, that would be good. If you don't mind, I have a question actually for Matthias. Your heat exchanger were actually very nice, and I would be curious to know what are for you the challenges to improve the process quality in additive manufacturing.
Okay, thanks for your introduction, first of all. I believe this beam shaping is very interesting and a whole new world. We didn't tap into that very much until now. You asked about the quality requirements for the heat exchanger, right?
Yeah, I mean, you were showing very nice pictures, and I guess that this is kind of an example of very high quality parts. And my question was, what do you think are the challenges to improve the quality and reach that kind of quality?
Well, for heat exchangers, I'd say the quality is there. So for air-to-air heat exchangers, definitely. We also have some heat exchangers for optics. So for LEDs, laser optics, some of our customers manufacture in serials of numbers of few hundred pieces, few thousand pieces. The main point for me is getting I'm exaggerating, it's getting down with the quality and the price. So our first customers have been gas turbine manufacturers, medical companies, aerospace companies. They wanted to have ultra high quality and full assurance of quality. And now we need to get more down to earth. We need to get down with the price, and also many customers can accept lower qualities actually.
Okay, that's a good point. And by the way, if you want to listen to beam shaping for any kind of application, we have also a meeting on that. That is the week after the next one, so Monday, if I'm not wrong. So check our website. Otherwise, if you rely on me, it's bad with dates. But Onno, very fast, because we have to go back to the agenda. Very quick.
Okay, very quick session also to Matthias. One of the things questions you raised is increasing demand. What are the top 3 things to do to achieve that? Because the 3500 systems is great and US machines are really reliable, I know, but let's be honest, in 30 years, 3500 machines is not what you want to achieve.
Yes, that's right. I mean, there are factories where there are twice as many milling machines, and we have 3D printers in the whole world, and we want to get there too. I believe what is important is to change the mindset in companies, but also to start at universities already, start the mindset of young engineers to embrace this new technology and work with it. And the other thing is to make additive manufacturing more easy, more standard, so that it can run on a manufacturing floor without requiring a PhD standing next to it. Those are very important points. And otherwise, I'd also like to know your opinion, because you're working in that market a lot. So you maybe have more experience in that and can tell us as a manufacturer what we need to do, what we need to change.
Yeah, great. Let's hook up after this session, and we'll.
Yeah,
I think we can talk for some hours about that. Yeah, very good.
Some hours, wow.
Yeah.
Then it's maybe better if we don't talk about it now.
Been doing it for 15 years, so some extra hours is not too difficult.
Yeah, definitely. It's very worth time to talk about this to improve production anyway. So now it's time for Fraunhofer, right? Fraunhofer IOF. So Eric Beckert, we have to let you roll on stage.
Okay.
There you are, yes. You can share your screen and the floor is yours.
Okay.
Yes, very good.
I will also report about the printing of optics. I will discuss a technology that has not been mentioned up to now. It's so-called inkjet printing. You all know inkjet printing from your home applications, printing your photos with the inkjet printer, but we talk about the inkjet printing of functional materials and structures. And I will now report about microlens array printing, in particular on very large areas. The motivation for, let's say, a large area, micro-optics can be found in, let's say, typical illumination and imaging systems. So you have projectors nowadays, even artificial sun daylight projectors or light homogenizers that make use of micro-optics. And if this is in a public illumination area, then you also very often have the demand on having rather large micro lens arrays that do such kind of a job. But you can also go to the imaging area where you have flat cameras and microscopes and things like that. So there are indeed some applications that really require going onto large areas, and by large areas I mean something like wafers bigger than 200 millimeters. Sometimes we even have requests to go to the meter dimension. So what is the approach that we are investigating? I told you we are investigating inkjet printing. So you know it from your home application. You have a functional material. In this case, it is not a color, it is instead an optical polymer. We use the probably well-known Ormocea material in our inkjet printer. We have a very special formulation of the Ormocea that makes it not only usable for the inkjet printing process itself, but also for getting rid of having a so-called solvent evaporation process. So you see the process flow on the right. We have a pre-patterned substrate. That is something very interesting. This is what the EPIC community can do for us. We need still pre-patterned surfaces. We have been in contact with Heidelberg, for instance, about that. And we print our optical material onto these pre-patterned surfaces, and simply by surface tension, the material forms a microlens. And by specifically formulating our optical material, we are even able to get rid of this solvent evaporation process. So we only have to do the UV curing of the printed material to create then the real microlens array. Of course, we do that in several runs. Sometimes you have even up to 1,000 droplets in one microlens. The big advantage of the printing process is you can really individually address each lens itself. That is the big difference to application processes where you have, let's say, where you have a predefined radius of curvature of the lens by means of your master. With respect to the inkjet printing, you can really individually address the radius of curvature of the lens simply by changing the dispensed volume on the pre-patterned surface. We use commercially available inkjet printing equipment. This is a little bit different than equipment that we have seen before. Nevertheless, it uses the same type of gantry systems for precision positioning of printing print heads and so on. And such equipment is available for large area printing. You know that graphics are printed on large areas, and now we can also print optics onto large areas. And the results that we actually achieve are really comparable to traditional, let's say, replication processes for microlens arrays. If we take a look on what type of lenses we address, it is, let's say, at the edge from microlenses to miniaturized lenses. So I'm challenging the two photon people a little bit here, since we are printing larger optics, I would say, still microlenses, nevertheless, rather miniaturized lenses. You see that we, depending on the radius of curvature and depending on the size of the lens, let's say a diameter of 1 millimeter, and radius curvature also in the range of 1 millimeter, and lens height in the range of up to 100 micron and even larger. So I guess that is a little bit too big for the two-photon polymerization. So you see on the left that we sometimes even place more than 1,000 droplets in an individual lens. Nevertheless, still we are able to get a very precise shape when optimizing the process with the deviation of the height and also the radius of curvature much less than 1%. And that on an area up to, let's say, 300 millimeter wafers, and we believe that can even be achieved on the meter range. And that actually already brings me to the end of my talk. You see a 300 millimeter wafer here in the end, completely printed with a microlens array onto it, and this is used for an artificial sun illumination application. So thanks for the attention.
Thank you very much for a beautiful presentation and a beautiful, beautiful last slide. I am very, very interested in what you can do for the others and the others can do for you, Eric.
Yes, so we are interested in materials, optical materials, that have the ability to be inkjet printing. And then I have already been talking about metrology aspects. I think not only relevant for inkjet printing, but for additive manufacturing in general. Metrology is, I think, one of the most underestimated issues in additive manufacturing. We, for instance, are interested in the precision of overlaid structure, but we also have the simple problem that we need to have an online monitoring of our drop ejection from the printhead, from the inkjet printhead. So metrology is the droplet volume still as it shall be. So process metrology.
For me, what really makes me excited about all the micro-optics manufacturing that I'm seeing now here, that I also talk at SUS Micro-Optics and with DVG and with Morphotonics and with all of them, is that now we are talking wafer level. And that's really what is really, really cool. That finally we can talk to the guys who make mobile phones, so we can put micro-optics here, a wafer level for the low cost. But I have so many companies making VCSELs. We actually have a meeting next in 2 weeks. We have a meeting on VCSEL manufacturing. We have all the VCSEL manufacturers with different wavelengths. Is the material the biggest challenge that you have right now?
No, it's not the biggest challenge. It's rather the reliability of the process. That brings me again to the metrology of the process. That is the biggest challenge. If you imagine you have an area of 1 meter, and if one lens on this meter fails, then the whole imaging or illumination system fails. So you really have to have a very high process stability of the process.
If you want to have a partnership on reliability and test, there is nothing better than my friends from Vigo in Galicia. And I have Camilo here to be the last speaker, sending us for having a great weekend. Camilo, thank you very much for being with us today. Muchas gracias. The floor and attention, everyone, is yours.
Okay, thank you. We're switching gears again, since we switched to another additive manufacturing technology. Do you see it okay, full screen or not?
Camila, I'm afraid you're sharing the wrong screen. So I guess you have 2 screens.
Okay.
Yeah. But he did it before. Very good.
Okay. Hi, everyone. So my name is Camilo. Thanks for the invite. I'm I am admin, Technology Center, but I am presenting today Integrate project that is on additive manufacturing process. My background is on laser-based manufacturing, but in the last year, I have been working on high power laser applications and systems technology. So at a glance, in case you don't know us, we are located northwest Spain in Vigo. We are a research institute, very focused on manufacturing applications, very industry-oriented research. And one of our core facilities is a laser application center that enable us to support industry and to make an informed judgment on the technical feasibility for different laser processes and applications. We are about 220 people, and our research areas can be listed there: advanced materials, smart systems and factory automation, advanced and additive manufacturing, that's the topic today. Also micro and high precision manufacturing, also laser-based, very active there, and sustainable manufacturing processes. So before going into the project, I would like to mention a bit, give a few words about this technology. It's supposed to be videos here as I show. So we are talking about direct energy deposition methods. So this technology fuses the metal or metal alloy using focused thermal energy provided by a laser or arc welding or other electron beam or other. So the machine or the robots or the positioning systems spreads a thin layer of the metal powder across the print surface, and the laser then traces that geometry of the layer. No? So one of the characteristics or the main characteristics of this type of additive manufacturing technology is that it's suitable to very large parts. The design freedom comes because you can manufacture over non-flat parts, so that is also very interesting. The combination of materials, since the material is either blow or wire fits, you can combine materials in different parts. And one of the other characteristics is that the shape, the resulting shape is not a net shape, so it usually requires some machining. So it finds applications on both reconstruction and repairing, that has been for a long time, known as laser cladding, but also new components and additive parts. So the project I'm going to talk about is called Integrate. It was awarded by the European Commission 1.5 years ago. We started its pilot lines on metal additive manufacturing. Since it was mentioned also from other speakers, but the importance in the additive field about the software solutions and the interconnection between the different stages. So the industry 4.0 and the automation importance. So what we are trying to develop here is a digital end-to-end solution that we compile or consider every step along the process and join all the data that is generated along this process. Present that later. We have 5 pilot lines. So it's a pilot lines very focused on industry uptake of these technologies. So those are listed here. I'll briefly comment on the drivers and the sectors. So we have first one of aeronautic for a molding tooling. Another one for that company, MX3D, for construction. They are using wire arc additive manufacturing. Another driver, especially in the aeronautic sector, that is one of the ones that is pulling for this technology, is the buy-to-fly ratio and the manufacturing components in titanium. And we have also 2 other applications in laser metal deposition. So that's the technology that we mainly work at EMEA, that is depositing thin layers either in molds or other manufacturing equipment for the steel industry. So this is the drivers. It's a very large project. We are 26 members. We cover from software developers, technology developers, sensors, quality control, down to the application-driven lines. I want just to mention the concept or the figure we have in this project, that is open pilot lines. So our research facilities, they will be able to provide a specific service on these technologies for industry in certain type of calls that will be released later on in the project. And to explain a bit more about on the specific application and our core technologies on EMEA, I use this simpler workflow, but I think it captures quite well the idea of the projects and some of the technologies we are currently developing at EMEA. That is in the product engineering phase, software related, but also covering the aspects of simulation and path planning and robot machine generation. That is very important for assessing and for assuring the quality of the parts. Then we have the build phase, obviously as similar as the parts are being manufactured, but we have developed in the past and recently quite novel advanced monitoring solutions, and that allows us to use that monitoring online to actually capture, to reconstruct thermally the history of the part, how that was built. And that is really important in this type of manufacturing, because they are long time runs for producing these parts and also for assuring the quality. So that information we are linking through this project and through several partners working on this with different stages of the manufacturing workflow, both with the simulation, with the resulting quality, with the mechanical and metallographic aspects, and so on. And then once the part is manufactured, it gets to the previous to final stage. Usually there's metrology and inspection Also, we're performing NDT, but optical sensors for assuring that the part is within tolerances, and even during process developments, those metrology sensors help out to keep the process progressing within tolerances. And then we are using all these steps and the data analytics also obtained from the metrology data to link with the simulation data. So in that way, it's like every little part through this interconnection, the interlinks is more well connected. So yeah, to sum up, on our side, focus on what we can offer is process application development. We have been doing this for a very long time for various laser-based manufacturing processes, process monitoring and software development for control algorithms and for embedded solutions for keeping those advanced processes within right quality. And then in terms of what we need or what we are looking for, we'll be looking for from the industry or from the end users, novel applications, novel materials that need to be, that can be additive printed. And then for the technology providers, we would like, there's a lot of room of some of the technologies that were mentioned here and covered in some of the EPIC events in terms of beam shaping, medium infrared sensoring or sensing, that is very important for these types of processes, as is thermal, and also metrology solutions, that also one of the key enable technologies for this additive manufacturing direct energy deposition methods to take on and reach widely the market. So those are for me the key points. And yeah, this is what I have. And thank you very much. If you have any question.
Thank you very much, Camilo, for closing the meeting like that. That was fantastic. You know, what can you do for the others? What can the others do for you? I think you know the drill.
Yeah, we can do for the others as we are a laser-based manufacturing research institute. So we can develop applications, work with novel technologies in terms of shaping, sensoring, scanning. This is what we can do, assess cutting-edge novel solutions. And what the others can do. So from the supply chain, yeah, I think I pointed out, but I would say novel laser systems, beam shaping, metrology and sensoring. Sensoring the process is very important, yeah.
Fantastic. Let me introduce you to some of the potential partners here, and we have to go all the way to beautiful Switzerland now. I go to Fabian Lutol. Fabian, what did you think of the meeting today, and what kind of collaborations, follow-ups would you like to do?
So first of all, thank you for having me here. First time in the EPIC meeting, and it has been fantastic for me. Really nice to to hear all of the people and see so many different things. We are doing R&D for the industries mostly, so we take technology pieces that we find, try to industrialize them. So we are also on both ends actually of the 3D manufacturing chain. So we use a lot of 3D manufacturing processes to actually generate things that other people can use from us, but we also build a little bit on it. So we also do inkjet printing, for example, which we mostly use to deposit functional materials on top of 3D printed, but also other things. Me personally, I'm mostly doing optics, so I was more intrigued by the previous talks actually, also the inkjet printing talk. And I think that there is a lot of potential also in material development. The other thing that I saw that could be really interesting is actually all the things, as was already mentioned before, going into the direction of Industry 4.0, like also machine learning things. That's also where we can contribute a little bit, but also use things from other people.
Thank you very much. And I think it's one of the cool things that you can do ever is to go to CSEN, to go to Neuchâtel and to see the kind of laboratories they have there. It's quite spectacular. And together with CSEN, we are making the micro-optics revolution in Europe. And I'm really happy to have you as a partner. Any final question, thoughts? because I have a couple of things to tell you. So while I was in the YouTube and I was talking to you and chatting with many of you in WhatsApp who were telling me I want to contact that guy, at the same time I was taking notes. Because in this meeting, you really learn a lot. And I really realized that with these meetings I can do offline, I can actually be typing while I have the meeting, and something I cannot do at the present meetings. And I took the summary slides that look a little bit like this. So in my opinion, this meeting was actually very well divided into 3D printing on metal and 3D printing on micro optics. I think there's a little bit of overlap on things that we can do together, especially in the positioning, but all the rest is quite separated. In 3D printing on metal, all the discussion was really towards process monitoring. I think this is really the key challenge that all of you have. I was amazed by the company NIT Europe and the process for, well, the cameras for the process monitoring. And they actually were talking about the kind of value that they have for 3D printing, and it was actually even numerized in terms of avoiding head heating, in terms of fully all the time control the laser beam. We talk a little bit about beam shaping, but in my opinion, no, not enough. I think that is the challenge for the optics part, and I think that requires a separate meeting, and in the meeting that we're going to have in Siemens, I really want to address this deeply. There is a lot to cover in the beam shaping. When we talk about the surface finishing, the combination with CNC process and other processes is something that we still need to address. There is a lot of room cover, and I love the presentation from EOB on that particular challenge. The biggest challenges from Onno was very clear, is increase the demand. The biggest challenge for EOS was very clear, is to go into lower resolutions. 100 to 100 nanometer is possible, okay, maybe, but that's really the kind of trend that we need to follow. The biggest, for me, highlight in the 3D printing on metal was a cognitive 3D, two materials at the same time. I put your picture there. That was awesome. Fantastic job. The second part of the meeting was more into 3D printing on micro optics. The revolution, the European revolution is micro optics. Remember that. We were talking about different processes: two-photon polymerization, inkjet printing, grip printing, direct laser writing. We talk about everything was towards the 100 nanometer resolution and below. And the questions about reliability and volume production were answered. So now it's a mature technology at wafer level, already ready to develop in seconds, as Ruth very well said, in seconds already lenses that can actually package micro LEDs, detectors, and pixels for the consumer electronics market. And that's a huge accomplishment. I think right now we have to really address all the different problems that we had. And there, the presentation from Nanoscribe was very clear, because they were talking about application on integrated photonics, on DOEs, microfluidic, and say, let's do rapid prototyping to validate the process with these customers. And to put as an example, I borrowed a picture from the presentation from my friend Christian, because there he shows some of the micro optics, customized micro optics that two-photon polymerization can enable. It is, of course, a technology that is driven by software, which is what I like. Photonics is a digital technology. So that's why I borrowed the presentation, the picture from Heidelberg Instruments. I will correct this, don't worry. I borrowed the presentation from Heidelberg Instruments. I put a Chronity 3D instead. It is really driven by providing software to design, and I think all of you, especially Multiphoton, Nanoscribe, Vanguard, are investing heavily on providing a design software compatible to CAD, compatible to other existing, and that's really what makes this technology very mature. It has been, in my opinion, a fantastic meeting, but what makes this meeting even better is the follow-up. So all of you are going to be introduced to each other. Also, the people in the YouTube channel are going to be introduced. A personal favor, when I introduce two companies, please follow up, answer the emails, and do your best to find a reason to work together, which is the EPIC policy. And it's also the EPIC policy to finish on time, so I have to apologize for 7 minutes late. Have a great weekend, a fantastic weekend. You deserve it. And anything you need, the EPIC team is here for you. Enjoy. Bye-bye.
Thank you.
Bye-bye. Thank you also from my side.